Hello, I am Tan Trung, a chemistry professor at the University of Utah. During the coronavirus pandemic, our university was forced to go online for all courses. This is part of an undergraduate physical chemistry course that I'm teaching, and we are almost finished the course, and I decided to collect these 4 lectures as part of these fundamentals for quantum chemistry and turn it to public so you can take advantage of it. And I hope you enjoy this. Again, we are practice social distancing, so I am self-recording this lecture and do everything myself, even making this pointer. You see this handmade. That's very interesting. Also, this lecture is chalk and board lecture, so nowadays it's not very common because many professors and teachers are starting to use more of the PowerPoint presentations and so on. So it's a dying practice, and but I hope you enjoy it. My students like it. Okay. So far, let's go into and review first before we move on. We start the class by introducing quantum mechanics, going to different simple system in quantum mechanics as particle in the box, the harmonic oscillator, the rotation in a ring on a rings, rotation on a sphere, and then get into the first simple chemical system, hydrogen atom. And for the hydrogen atom, we can solve the Schrodinger equation for exact solutions. And we get the energy levels and the wave functions. And wave functions depend on 3 quantum numbers, N, L, and M. And these wave functions, we often call it atomic orbitals and denote as 1s, 2s, 2px, 2py, 2pz, and the D and the F functions, and so on. These orbitals have known explicit mathematical expressions for it. Right? Then we move to the many electrons atoms. We discover the electrons have the intrinsic spin. So either spin up or spin down, they have 2 spins. And we call it alpha or beta, or up or down. Also that we find out that there is a Pauli exclusion principle, saying that for each electrons, it have a unique set of quantum numbers that N, L, M would representing atomic orbitals, and in its own spins. These 4 quantum numbers must have unique set, just like its ID number. Okay, from this, we can realize that each atomic orbital can have at most 2 electrons, right? 1 alpha and 1 beta. Also, the many electrons wave function must obey the anti-symmetric conditions. And this is part of the quantum mechanics postulate, the last postulate. So what that means is that these multi-electron wave functions, if we interchanging any 2 particle, 2 electrons, it changes the sign. So for example, here I'll change 1 and 2. So over here, 2 switch to 1. Then it changed the sign, minus sign. Okay? And also the many electrons wave functions, we don't know the form for it, and we find out that Slater determinants approximation is a good approximation for it. And in solving the many electrons atoms, we have to introduce the central field approximations. These 2 approximations I will discuss more later in this lecture. Once we do that, we were able to solve for a set of atomic orbitals have a similar shape as that of the hydrogen atoms, but a different size. And this we also denote that by 1s, 2s, 2p, and so on for that. So that's what we've done so far. We also went on to a very simple molecular system, H2+, to introducing the Born-Oppenheimer approximation and so on. But let's start over again. For a general molecular system that I have n nuclei and n electrons, okay? The full Hamiltonian operator for it consists of these 5 terms. Okay. Now, if I write it in atomic units, all of the constants, the Planck constant, the mass of the electron, 4 pi epsilon 0, the electron charge all go to 1. So I don't have to write. So make the equation cleaner and easier to see. So this Hamiltonian is written in atomic units so that the first term is the kinetic energy of the nuclei. So it's just sum of all the kinetic energy of all nuclei. And the second term is the nuclear repulsions. It's just a Coulombic. So I sum over charge A, nuclear charge of A, nuclear charge of A over the distance. And I make sure I don't double count them, B less than A. So this double sum here, do not double count between A and B. And the third term is the electron, the kinetic energy of the electrons. So I just sum over the electrons and this kinetic energy operator for that. The fourth term here is the nuclear electron attractions. Again, it have a simple Coulombic interaction. So I sum over the nuclear, I sum over all electrons, the attraction, so nuclear charge and distance between the electron I to the nucleus A. The last term is the electron repulsions. Also, it does have the Coulombic forms, so sum over I, sum over J, 1 over Rij. So the distance between 2 electrons, and when I sum over J, J less than A. So again, avoid double countings. Now, our task in quantum mechanics is to solve the strong equations. We're putting that Hamiltonian into the wave functions, unknown. So for the energy and that unknown. So this is the second order partial differential equation. It looks very complicated. The wave functions here depended on the coordinates of all the nuclei and the coordinates of all the electrons, and it's unsolvable. Okay? It's too complicated and unsolvable. So we go in there and we start making a different type of approximation. We start breaking the huge problems, the complex problem, and we break it down to smaller. So we start making approximations. The first approximation is the Born-Upper approximations. That's recognizing that the nucleus, the proton is about 2,000 of the mass of an electron, so much heavier. So the nuclei are heavy, and the electrons move much faster. So a metaphor for this is a cow walking and a bunch of flies moving around it. So now try to solve for the motion of a cow and a flies would be very complicated. So, but a cow moves slow, flies move very fast. So we can say that, hey, these motions of the nuclei and the electrons can be separated, or I can assume a cow stand and solving for the motion of flies, and then getting the average potential of the flies where they are, and the cow move, and from there. So same things here, saying that, hey, I can separate the nuclei motions from the electron motion and solve them separate. And I start off solving the electron motion first, the electronic Schrodinger equations, and the solution of the electronic Schrodinger equations allow us to use that result to go and then solve for the nuclei Schrodinger equations. Okay, one at a time. So I'm breaking the first problems down into two: electrons separate and the nuclei motion separate. That come from the Born-Oppenheimer approximations. Now, quantum chemistry focus on solving the electronic Schrodinger equations. What is the Hartree-Fock method? Well, the Hartree-Fock method assumes it for a fixed molecular geometry, again, from the Born-Oppenheimer approximations, then solve the electronic Schrodinger equations. So we go in there from the four Hamiltonians, collecting all the terms that involve electrons, kinetic energy of the electrons, the potential energy of the electrons, attraction with the nuclei, the electron repulsions, and conventionally we also including the nuclear repulsions because it's a fixed geometry, so this term is constant. So we take them along. There is an advantage to that. So now the electronic Schrodinger equations is the Hamiltonian solving that wave function equal to E psi. The energy here now with the inclusion of the nuclear repulsions that have a term potential energy surface. It is a potential govern the motions of the nuclei. That term here go directly into the nuclear Schrodinger equations. Okay, and last time when we talked about these hydrogen plus, well, that's potential curve since hydrogen plus have only the nuclear distance, so it becomes a potential curve instead of a surface, multidimensional surface. See, so that's a potential curve. So you see how the two nuclei, when you push them close together, they repel up and they pull them, so they have come to a certain equilibrium. So these are molecular in the equilibrium distance here, and then when they will pull apart, they will be separated. So these are the potential curve, and for multidimensional, for the molecular systems, we have a potential surface similar that govern the motions of the nuclei. Well, the problems, right, that the electronic wave functions is unknown. So, well, we continue to make approximations. Right? We know that these electronic multi-electron wave functions must obey the anti-symmetric conditions, which mean the interchange between two electrons would change the sign, and definitely it must obey the Pauli exclusion principle. So we use slider determinant approximations. A determinant have two properties that would satisfy these conditions, earlier condition of the wave function nicely. That is, if the two row or columns in the determinant that's identical, determinant is 0. So obey the Pauli exclusion principle. If you switch any row or any columns of a determinant change the sign. So again, obey the anti-symmetric conditions. So slider determinants is a good approximation to a multi-electrons wave functions. And we assume it is just for simplicity, that these molecular systems have only one electron configurations. Then one arrangement of electron in the orbitals. Usually it is in the ground state. So with that one electron configurations, we can write out the wave function is 1 over square root of n factorial. This is normalization constant. And the determinant, we order in a row the orbitals along this way, electrons along that way. So you see K1, K2, Kn, and electron 1, electron 2, and other electron n. So chi here is termed as a spin orbitals. And the spin orbital is just a spatial molecular orbitals times a spin to ensure that each electron have a spin orbitals. Okay, and now we get to the next point is we don't know the molecular orbitals form for it. Right? So we started getting step by step, solving step in step. We get into the multi-electron wave functions here. We get into the unknown form for the molecular orbitals. So we make the next approximation, the molecular orbital approximations. Now, the logic for this is that molecules consist of atoms, and atoms have atomic orbitals, as we mentioned in the review in the first part of the lecture. So therefore, molecular orbitals must consist of atomic orbitals. That's simple logic, right? And the simplest way of approximation would say that, well, the molecular orbital would be some linear combinations of the atomic orbitals. So that's, we call it LCAO approximation. Right? So we ran out a molecular orbitals. Psi I is some linear combinations of the molecular orbital phi mu. Okay? And this is the MO coefficient. It's a weighted coefficient. It's how the contribution of that atomic orbitals in that molecular orbitals. Okay? So this phi mu here is a set of atomic orbitals. We call it the basis set. So for example, we have a hydrogen fluoride here. The simplest, or at least the minimal, I would need to have the 1s for the hydrogen electrons, and I would need 1s, 2s, 2px, 2py, and 2pz for the fluorine. So these form the atomic orbital basis set for this. And this set here, these atomic orbitals here, can have more than the numbers of the electrons, right? So if I have k atomic orbitals, I would make k linear combinations, or in other words, I would have k molecular orbitals. Now, the set of molecular coefficients is unknown. How are we going to determine this? Well, there's help. We can use a variational principle for it. Okay? So we can apply the variational principle to determine the set of MO coefficients. Variational principle saying that the average energy calculated from any guess, right? Any approximate wave functions, multi-electron wave function, this is a slightly determinant that we mentioned earlier over the Hamiltonian operators and by this integral over all space. This is part of the quantum mechanics postulate. So this for calculating the average energy. So the average energy always greater or equal to the exact energy. This is a great news. Why? Well, what that means is that if I have What that means is that the exact energy from here and the average energy always somewhere above. So all I need to do is to minimizing that energy to get the best possible average energy. And that would be a minimization problem. So I go and take the partial derivative of that average energy over all of the MO coefficients unknown, set it equal to 0 to minimizing the average energy, and from there to find the optimal set of MO coefficients. Right? So now we go in and take partial derivatives out and set it equal 0, and we get a set of equations and a set of unknown. Well, the problem is when we done that, we find out that due to the terms of the 1 over Ij that exists in the electron repulsions, these set of equations, we cannot factor that out and set equal to 0 and so. So we have to make another approximations we call central field approximations. The central field approximation said that assume that each electron can only experience the average potential of all other remaining electrons from its locations. Okay, so a metaphor for it is a blind man sitting in a classrooms. He cannot see all other students sitting in other chair, but he can feel the potential for their existence in his skin where he sits. Right? So he can find a good sit from the potential he feels from our students that already sat in the classrooms. That is their metaphor, an interesting metaphor for it. So this metaphor saying that, well, the electron eyes, the potential that's in the electron eyes is that I integrate over the electron J, the densities, times is a little charge in a cubic of little charge L over the electron J, and to the distance to the electron I, and integrated all space of the electron J, and then I'll sum all other electrons, J electrons, that not equal to I. Now, just for a note, remember the electron repulsion have a very explicit form, right? Sum over I, sum over J, 1 Rij. So it required that you knowing all the corners of the J. Here, this potential, one is the electron I's, it depends only on its I coordinates, the coordinates of the electron I's. Okay? So, now, what is the consequence of this central field approximation? Well, the central field approximations, now the potential for electron just sum over the potential of all electronites, which is a 1 electron term. Sum over it. Simple, right? Now, consequences, we started out as electronic Schrodinger equations of n electrons. This is only one equation. The wave function is n electrons, so this one equation, n electrons, and it's unsolvable. We cannot solve it. And we making a series of approximations and get to the central field approximation, and it turned out that these solutions to the variational problems, partial derivatives equal to 0 here, would have to satisfy these eigenvalue problems, 1 electrons, Fi chi equal to psi I chi I. This is 1 electrons. right? Where E of I, here is the orbital energy, I, and F of I is a Fock operators of electron I. This is a one electrons operators. It's similar to a hydrogen atom. And one electron problem we know how to solve. So it become N, right? N one electron problems, and it's solvable. And a very interesting metaphor for it is that when I ask you to go and breaking a bundle of chopstick like this, and you try to break it, and it would be very difficult. I wouldn't be able to break it, and I don't think anyone can break it. But if you can find, I introducing 3 approximations, the slather determinants approximations, the linear combination of atomic orbital approximation, the center field approximations. All I have done is I break it out into the separate sticks. And all I do is it's easy. I can break one stick at a time. See that? That's the idea. The only problem with this, though, since the Fock operators here depend on the set of orbital J, that not the electronite. And Fock operator of electron pi depend on all the orbital J to calculate that center field potential. So therefore, this set of eigenvalue problems you need to solve iteratively until all the orbitals and the total energy converge. In other words, they have little change from one iteration to the next. And for that reason, this theory is also known as the self-consistent field theory. So we solve for the field until it's self-consistently, right? In other words, iteratively. So that is the nut and bolt of the Hartree-Fock theory. And I hope that you appreciated that we started out form one equations, electronic equation for n electron that we cannot solve. We start molecular systems, and we start introducing first the Born-Oppenheimer approximation to break out the nuclear and the electrons motions. And then we focus on the electronic motions. Then we start introducing a different approximations. Right? We assume that the multi-electron wave function have a form of a single slather determinants of the spin of the molecular orbitals. And we don't know the form for the molecular orbitals, so we assume that molecular orbitals is a linear combination of atomic orbitals. And then in solving the molecular orbitals to find the best set of molecular orbitals that get the best energies possible for that gas wave functions, we find out that we have to introducing another approximation called center field approximations, and then we break the problem down to an individual one electron problems that we can solve. Okay? Now, next lecture we can move on to go and addressing the errors of these approximations, go beyond these Hartree-Fock theories, and look at all the errors, how we can improve on the Hartree-Fock theory.